Good morning. Before we get started with this lesson today, I just want to let you know that this will be the very last video lesson of the course. And for you, it's particularly exciting because this could also be the last math lesson that you ever need to sit through. So congratulations for that. We're going to get started now. We're looking at graphing a Fourier series approximation. So I've spent a considerable amount of time showing you how to use mathematics, and in particular the integral, to take any periodic function from its time domain graph and to transform it by using a Fourier series into its approximation. So for our purpose here, I've elected to use Waveform 5. So here's a drawing of Waveform 5. I just did this one in Word, which is why it's a little bit imperfect, but I took a peak voltage of 100 volts and a period of 50 milliseconds, and I've graphed two periods of that waveform. We had already developed these time domain equations in a previous lecture, so I've included those here. Now into these equations where we have Vmax and capital T, I went ahead and substituted 100 volts and 50 milli respectively. And in doing so, I got these equations, 4000 T and negative 4000 T plus 200. So the period now here is 50 milliseconds, so I've also adjusted these time values. Okay, so now we have equations specific to the two periods of Waveform 5 graphed here. I went ahead and took the final answer for the Fourier series of Waveform 5 and included it here as well. Now into this expression, I also have substituted 100 volts and 50 milliseconds. Just for clarity, here, for example, I did 2 divided by 50 milli is equal to 40. All right, 6 divided by 50 milli is equal to 120, and so on. Okay, and again, everywhere else, I made sure that if we had Vmax, we substitute 100 volts, capital T, 50 milli was substituted. Okay, so now for Waveform 5, we have these two representations, and they are equal representations. You can represent the waveform with these equations. We call these time domain equations. Or you can represent that exact waveform with this Fourier series. Okay, now what I've done on the next page is I've taken only the first 5 terms. So the constant term and these 4 cosine terms, and I have graphed them. Now I used Graphmatica. So it's graphmatica.com. It's a free downloadable graphing software, but I encourage you to use any graphing software that you like for this purpose. Okay, so it says here, if the first 5 non-zero terms of the Fourier series are graphed, so 5 terms in total only, an approximation for the waveform can be obtained. So here is the graph that I obtained, and this is the equation that I typed into Graphmatica. So there are It's a very easy software to use, but there are a couple of things you have to be mindful of. For example, we have to include y as the dependent variable and x as the independent variable. Pi, you can see pi is pi, and so on. So you can take a very good look comparing this equation with this one to see some of the nuances of the software program. Okay, but here's the key. This is what I'm trying to really drive home with this lesson today. We only used one constant term and 4 cosine terms, and look at the good approximation we have for the waveform. By the way, this is exactly 50 milli here. It might be hard for you to see the numbers on this scale. This is 50 milli, so that's exactly 1 period. This is 100 milli here, so 2 periods are graphed, and look at that brilliant triangular shape. Here is 100 volts. It's not quite up to that max here, and you can also see it's not quite hitting that horizontal axis at these points either, but it's a darn good approximation considering how we made the graph with one constant term and 4 cosine terms. So it's quite a good approximation. Okay. These are approximations for waveforms 1 and 7 and 8 respectively. And again, it's amazing to me that you can approximate a square waveform. And again, this is using 5 terms in a Fourier series only. So how do you get a square waveform? By just using simple sine and cosine terms, and only a few of them, right? And this is, again, waveform 7, waveform 8. You get a pretty decent approximation considering we've only used 5 terms. So I've had students in the past take this to another level and maybe type in 10 terms just to see how this really flattens out. Okay, and it won't be a requirement for you. I'm going to be asking you to graph one waveform and using 5 terms. Okay, but more details of that will follow. But the approximation gets better and better the more terms you put in. And of course, it's an infinite series, so it would take an infinite number of terms, for example, to get a perfect replication. But for electronics and for music in particular, you find that you can just use a finite number of terms and get a very, very, very good replication. Okay, so I've included here also hints for using Graphmatica. So this is the equation that I wanted to type into Graphmatica. This is how I did have to type it into Graphmatica. And then you have to also do this. You have to select View and Grid Range in order to adjust the domain and range. So for example, the waveform 5 that I graphed, remember that the period was 50 milliseconds. So to include 2 periods, I needed 100 milliseconds. So in theory, I would therefore go from 0 to 0.1, but you can see I've gone just a little outside of that. So I went from negative 0.001 to 0.105, and that's to ensure that when it was graphed, we would see the axes as well as the numbers on the axes, okay? So you can't go directly from 0 to 0.1. If you need to show 100 milliseconds, just go right outside of that domain. And then the same thing for these numbers. This waveform, remember I needed to show from 0 to 100 for the voltage. So again, just a little under 0 and a little over 100. So you can fiddle around with that a little bit, but the point is you definitely have to adjust your grid range, it's called. Okay, only after adjusting that grid range will you be able to see properly the graph. And finally, make sure that this ends up saying time. I've got here time in seconds versus volts, okay? Included title. So the title I wrote here was first 5 terms of Fourier series for waveform 5. So I'd like you to do that. And this is how you do it. You go to options, graph paper, and labels. Okay, so your class is going to be working specifically on waveforms 1 and 7 and 8, and I've included those series down here. I've only included the first 5 terms of each series down here. Okay, and then I made various period and voltage combinations. So you will use the chart to figure out which waveform you're working on and what your specific period and voltage will be. Okay, so just to give you a quick example, this is Nathan. Nathan's going to be working on waveform 7 using 50 milliseconds as the period and 80 volts as his maximum. Okay? Okay, but I will post lots of details about this little portion of the assignment shortly. I will say that when you go and do the assignment, I am welcoming you to adopt completely this format. So exactly the same language, exactly the same order, exactly the same content, except of course you will have to change this to a 1, a 7, or an 8, change the drawing, change all of the equations, and your graph, of course, will be unique. But you're welcome to just go right into this document. If you like, I'll put a Word copy as well as a PDF copy. You can go right in and alter it for your particular waveform and your period and your maximum voltage. Okay, so again, the point of the lesson today was that kind of, isn't it mind-blowing that any one of those periodic, well-behaved functions that we looked at can be represented by using only a constant in some cases and some cosine and or sine terms. So any one of those waves, the square waves, the triangular, the sawtooth, even the half-rectified sine wave, and so on, they can all be approximated by a Fourier series, which uses only sine terms, cosine terms, and sometimes a constant. Okay, thanks so much, guys. Have a good day. I will be posting all kinds of details about your final assignment.